Alright, welcome back. Let's finish up these slides on trees. So we learned a lot of fun traversals, all these bad boys. I would like to start off today with a question for you, see if you can remember them all. So here's a tree, and the root is in the place you would expect it to be, so there's the root. You tell me, what order would all the vertices of this tree be visited in a post order first, post order traversal, then pre order, then in order, and then breadth first, please. So let me go to all the relevant slides if you'd like to see the definitions of all those again. So there's pre order, post order, there's in order and breadth first, and we did some examples of each of those last time. So hopefully that was all the information you needed. So give that a try, and then I'll show you how I think about it. I'll do it a little bit faster, though, than I did last time. So in a post-order traversal, remember that the rule for post-order is going to be children before root last. All right, recursively post-order your children, recursively visit your children before you. And so if this is a binary tree, it's going to be like, let's do it left, right, then root. All right, so for post order, will be like left, right, root. Where when I talk about children, I mean recurse. So what are we going to do for this tree, calling it initially at the root? It's going to be recurse left, recurse right, hit the root. Okay, that's how that's going to work. So that's how I think about it. So left, right, root all the time. So this one, all right, so now this is a smaller tree rooted at B now. So again, left, right, root. Left, right, root. So D and B. The right was blank. So D and B are first. That's how I can do that. So that was left for the outer tree. Then right, now we're going to process this tree, which is going to be another left, right, root. So left, right, root. So this is the inner tree. So again, left, right, root. So G, E are next. See that? G, E. And then that was the left. Then we do the right, F, for the C tree. And then the root, which was the C itself. And so then we did left, we just did finish the whole right subtree, and then root for A. See that? That's how I like to think about it. I'm trying to like keep the stack in my mind. So that's post order. Let me make sure I didn't make any mistakes. Yep, looks good. And now let's do pre-order. So pre-order is when you do your root before processing your children. So if it's like this. So if it's a binary tree, we're going to do root, and then we'll do the children in left-right order. So root, left, right. That's how I'll think about it. So root, left, right. So, okay, the first thing's A, then root, left, right. So A, then left, all right? And this, again, is a smaller tree, root, left, right. So root, left, right. So D, and then, B, and then D. See that? So that was root. We did the left. Now I need to do the right, which, again, smaller tree. Again, root, left, right. So C, left, right, and that's a smaller tree. So again, root, left, right. So E, G blank. So that was root, that was left, and now I need to do right, which was F. Okay. Do you believe that is looking good? So that's going to be your pre-order. And then in order, I didn't make this easy on us. It's going to look a little weird. Not in any kind of alphabetical order or anything, unfortunately. But that's okay. We'll do it together. So in order has to be, for a binary tree, it's going to be left, root, right. Okay, that's how that'll work. Left, root, right. Left, root, right. So let's do that together. So okay, in order for this tree is going to be left, root, right. So all those subtrees are being visited recursively. So we're working on this one first. So it's going to be left, root, right. So then first it's D, then B. So that was that subtree, and that was left. Now we can do the root A, and then right for the outer tree. So that was left, root. Now we do right. And so again, that's another smaller tree. We're going to do left, root, right again. So left, that's that one, smaller tree. So it's left, root, right. Left, root, right. So G. Blank does not get printed. G-E. So that was left. Then we do the root C, right, F. See that? And that's looking good to me. The last one I made easy on us. Did you get that one? So for breadth first, you're just going in level order. assuming you add your left child before your right child. If you're building up that queue, it's really just you're visiting everybody in this exact order. Boop, 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 boop. So it's just the alphabet in the way that I did it. So that's your breadth first. That's going to give you level order. Okay, so that's finally something easy to write down. A, B, C, D, E, F, G. You can just read that off. Okay, so that's all those answers. Please yell at me if you have any questions about any of that. That's one good review question. And then here's another good review question. In essence, when you're trying to think of algorithms for trees, you're trying to come up with some way to do something to a tree or operate on a tree, most of the time it's going to be a recursive algorithm because you want, like you're doing things on a smaller tree, which makes sense to do the same, to solve the same problem on the smaller subtrees that make up a tree. So you can think of recursive algorithms on trees as just some kind of traversal, because at the end of the day, the traversal is recursive, right? Every traversal is recursive. It's going down subtrees. It's just like, which order do we do things in? Like, do I need my answer at the root first and then feed it down to the children? Or do I need the children's answer first and then use it for myself to build up a bigger answer? Usually you're going to do post order. In essence, on most trees, you're going to probably want to do post order. Figure out what's going on in the subtrees and like use that plus your root to build some bigger answer back. And so a lot of recursive tree algorithms, they look like a traversal in specifically post order. Okay, here's post order. See if you can take this code, because this is what it looks like, right? Take this code and try to adapt it, change it so that like instead of just doing processing, instead of that, adapt it to always be giving back the shortest distance from the root to some leaf. Any leaf, right? We want the shortest one, the minimum distance from the root to a leaf in a tree, all right? And so you can think about that in terms of smaller problems, like you can assume it's gonna give you the right answer back for a subtree, and it needs to give you back a value of that length, okay? So here's an example tree. So let's make it a binary tree. The things at the nodes don't matter because we care about like distances, right? So like here is a tree. Let's go a little bit further. Boop. One more level, let's say. So we want the shortest distance from the root to a leaf, which is 1, 2. So go that way, right? Go from there to there. Does that make sense? So that's what your program should return, and you can do that recursively because like if this is the root, you can make recursive calls, right? You can go post order, essentially. Go left, go right. What's it going to do on these? Imagine what your recursive algorithm is going to return for those smaller trees and see if you can use that answer to build up your answer for the bigger original call to yourself, right? So see if you can get that working. It's a fun idea. It's a cool thing. All right. Let's see if I can make this tree a little bit bigger. That could have gone worse. That's not too horrible. So, okay. Honestly, you don't even have to think about it like post order, but it's really, you do want to process your children first. You want to call yourself, get the shortest distance on the smaller subtrees first, because like what's going to happen? You get to assume, thanks to the magic of recursion, when you call your algorithm on this smaller subtree, it's going to always give you back the right answer. It's going to give you back the shortest distance from a tree rooted here to its leaf, which is going to give you back, this should be giving back 1, right? It's 1 distance from that root to that leaf. When you're zooming in and focusing on the tree rooted here. Okay, so that's going to give you back 1. You can assume that's going to give you back 1, and then you can assume that this recursive call down on this sized subtree, it's going to give you back the shortest distance from the root to a leaf, and the only leaf is down here, so it's going to give you back 1, 2, 3. You get to assume it's going to do the right thing. All right, and your job is to use those answers to build up the right answer for the full original tree. So what's the answer for this one? What's the length? What's the distance from the root to the leaf? It's this one, right? 1 plus, it's 2. And you can get that from these answers, can't you? You can get it by taking the minimum side, because this is the shortest subtree. See that? The shortest subtree distance. And then, well, that was when it was rooted here. If you want it rooted here, you have to add your one edge, the one edge that's separating you. And so it's going to be 1 plus 1. Right? It's going to be your smallest thing plus another edge to get to you to this original size tree of 2. That makes sense. So that's how that should work. And so that's pretty much your recursive case. We'll call this min dist on some vertex v. And so you do have to think about like base cases and things, but like that was the recursive case for sure. And then the base case is like, what do you do with that? So like you're going to recurse down left and right, left and right. Like here, like what do you do on this tree? What's the shortest distance between a root and this leaf here? You could say, well, that's 0, right? It's already a leaf. So maybe that could be your base case. You could also consider the empty tree, the null pointer, to be like a -1 distance because it's not a leaf at all. I don't know. But I think this is a good stopping point. If you are a leaf, you see how that's a base case? Like there is no distance from you to a leaf. You are the leaf. So if V is a leaf, if I can spell leaf, if it's a leaf, return 0, because there's no distance. Otherwise, we're going to do a loop, or essentially, because it doesn't have to be a binary tree. We're trying to modify this, right? For every child, W of V. Recurse. Call your min-dist, because that's what we are right now. So call min-dist on that W, and save the minimum of all those W's. Right? We want like the shortest way to get down to a leaf. That's the minimum. Save the min result. We're calling ourselves recursive. It's really post order though. Save the min result. Because now we're kind of looking at our own node, even though we're not looking at our data. We're like, okay, consider ourselves now. What's our distance? Well, the answer is the minimum distance, like the 1, plus 1 more, because you have to add an edge for us to get to our bigger tree, to get back to ourselves. So what we return in the recursive case, return min, that min value, plus 1. Okay? Does that make sense? I hope you're getting better at these algorithms. Recursion is fun, right? So yeah, if we're good with that, let's talk about a magical thing called spanning trees. So a spanning tree in a graph, so if your graph is connected, it has to be connected to find a spanning tree. So if you got a graph and everybody can reach everybody else, okay, then you can ask for a spanning tree. It's like the minimum number of edges that will be able to still link everybody. Okay, so you gotta have a connected graph. It's a subgraph. A spanning tree is a subgraph that contains all the vertices and is also a tree, right? Because if you added any more, you'd add loops at that point, and it's unnecessary. That's like the minimum thing that's connected, which would be a tree. All right, so here's a bunch of, let's see, how do I want to say this? So it's got to be connected, and it has to hold all the vertices, and it also has to be a tree. Okay, so you know how many edges it must have then, given what we proved before. So here are 3 example spanning trees of the original graph. So the original graph is just like, pretend all the red ones are also black, like the whole graph is all those, red plus black. So this is the same tree 3 times, and there's same graph 3 times, and there's 3 different spanning trees. Okay, there's this one, like they're all still connected. If you have just those, these are all still connected. You see how they're all trees still? They're all trees, free trees. And then like these ones, there's another way you can connect to them. Like you got options. So that's what it means to be a spanning tree. It's a useful thing, right? You want to have the minimum amount of connections and still be able to get everywhere. That's a important thing you'd want to have. Like if you're building a road network and you want to save money, or you're building a computer network and you want to save on cables, right? So that's a thing that we care a lot about. And yeah, so you're kind of making trees out of graphs. And where I'm going with that is there's a lot of ways to make trees out of graphs. All right, so now let's go back to those graph traversals, the DFS, the BFS stuff. Now we want to talk about those in terms of trees, because every time you take a traversal, every time you go through a graph, it's discovering the graph, it's walking through everybody, it's visiting every vertex from a starting vertex. And the way that it visits things and does not duplicate work is by creating a tree. It's creating a spanning tree. You see that? That's the idea. It's creating a spanning tree with a graph traversal. So, assuming your graph was connected, and it usually is. So let's look at the BFS and the DFS slides from graphs really quick, just to remember what's going on there. And we are going to notice, if we squint hard enough and remember, do you see, I kind of said this before, if I change my color real quick, to rainbow, of course, you see how there's a tree. We're not having any loop. See that? So depth first. It's making a really long tree, like very long edge down to the leaf there. Your min-dist function will give back a large value, but it's making a tree. It's totally making a tree. And then also, we were using a stack to do that. And then also for breadth first search, it was also making a more reasonable looking tree. So like it's trying to stick close to the original thing. But do you see how it's building a tree? It's not making any, it's not going past any extra edges because it doesn't need to. That would create a loop. Like it's never going to follow this edge right here, for example, because that would create a loop in its visiting path, and that's unnecessary. We've already seen E or we've already seen F by the time we got there. So it doesn't follow that edge. It follows the minimum amount of edges, and just to see everybody, and that means it's looking for a spanning tree. Isn't that cute? So that's fun. Graph traversals do that. And then depth first search, like we had here, it was using a stack, but as we know, stacks, we have one special kind of stack, and that's the function call stack. So instead of using an actual stack data structure, we can actually program DFS recursively and just use the function call stack as the stack. So here's the recursive DFS. Let me try to flip between them quickly. So we have to like take out visited as like a global variable because we have to keep track of that, and it needs to change in the outer places too. So like we'll make that global, and then it's just like this is what you do, and you're not pushing anything. It's just like instead of pushing, you're making a recursive call. That's the idea. Okay, that's what's going on there. And so if you flip past these quickly enough, you can kind of see what's going on and the differences and how it's working. But let me just give you an example. Here's the original tree, same that we were using. It's got the same time complexity, by the way, and it's using the function call stack implicitly instead of an explicit stack data structure. So yeah, let me just show it to you that it's going to do the same thing. But let me see if I can remember. Like this is our graph G right here. That one. This is our graph G, and we'll start at A again, and hopefully I can remember. Maybe we're gonna like do it in alphabetical order. I'll try to convince you that we're gonna get the same answer. Okay. So we have a visited set. And we have a function call stack, and that's like where we are right now, what we're looking at. So originally we're going to call DFS on A, right? On graph G, looking at vertex A right now. And it's not in visited. So A is like, all right, if it's not in visited, we're going to add it to our visited set, do what we need to do, add it to our visited set. So A has been seen. It's the very first thing. And I'm just convincing you that this way is exactly the same as the other way. It will also create a spanning tree, so look for that now. So A has been visited, and then for every adjacent vertex that is unvisited, we're going to add that, because we did that. We fixed this, right, for breadth first search. That was saving us some time, so we're going to make that change as well. We're going to, oh gosh, what have I done? Oh no. That's so silly. I don't know how I did this, sorry. Let me see if I can undo, no, there it was. So I somehow deleted that. You have to call DFS. That's very important. So we're calling it with A first, and let me see if I can recreate what I just did here. So there's function call stack. We're calling it with A first. Visited set now holds A. That was the first thing that we saw. Okay, so holds A. That was number one. Okay, and then for every adjacent vertex that is unvisited, and that's everybody right now, B, C, and E, we're gonna make a recursive call. So let's just do it in alphabetical order. Let's say that B comes first. We're going to call DFS on B, also remembering to go back and call it on C and E as well once that returns. Okay? So we're going to call DFS on B now. And so function call stack B, we're calling it on B. We're not done with A yet, right? Because we still have to process the C and the E from that one. So like we're sitting right here on the call to DFS on B, but we still need to go through the rest of this loop for A. Okay? So now we're at B. And, all right, B has not yet been visited, so we'll visit it, add it to our visited set, B, and then it was the second thing we saw, and we saw it through this edge. Okay, so we're trying to build that spanning tree. You can remember that if you need to. That's something you can save if you want to generate the actual spanning tree. So there's that, and then for every adjacent vertex that is unvisited, so A has been visited, so that one doesn't count right now. It's going to be D and F, you see that? We are going to make that recursive call. So we're going to make the recursive call. Let's do it first on D. Let's do alphabetical order. So D first, and then we still have to, like from B's perspective, it's still waiting in this loop to also run on F because that's unvisited. Okay? So that's the idea, and let's make it happen. So now we're at D. We're trying to call DFS on same graph G for D. This is our graph G right here again. Let's see. And so, yeah, we haven't seen it, so it's not been visited. We're going to add it to our visited set, D. It's the third thing that we saw, and we saw it through B, through this edge, right there, okay? And then for every adjacent vertex for D that's unvisited, but we've seen all of them, we've seen B before, we're going to make a recursive call, and so this is like a base case. We're done. Nothing more to do at D, like pop it off the stack, and then we return back to where we were in the recursive call to DFS at B. So now we're back at B because B was trying to visit D recursively and then F recursively because we were in this loop. Now it's time for F. Okay? So now we're going to make the call at F. And so that's kind of how the stack is working right there. This is the top of the stack, by the way. And so now we're back here. We have not seen F before, so we'll visit it, add it to our visited set. It is going to be the fourth thing that we've seen, and we saw it through this edge right here from B. Okay? And then again, for every adjacent thing that has not been seen before, so B's been seen, that doesn't count, but E is not. We're going to add it to our, not to our stack explicitly, but we're going to make a recursive call. Try and DFS on E now. See how that's working? And then here, E has not been visited, so we'll visit it, add it to our visited set, do whatever we need to do. Doing some fancy computation probably. And it was the fifth thing that we saw today, through this edge from F. So it's taken the long route for sure, because it's depth first, right? So breadth first would have added this edge from A, but we're not going to do that one here. And then we're going to recursively visit every DFS on every adjacent vertex, but we've seen F already, we've seen A already. No more things that we need to do at E, so E is done with its work. It'll be popped off the function call stack, and of course, I have lost eraser privileges for my tablet, and I don't understand why this happens. So now we're back at F. And have we visited everybody that's adjacent to us that's unvisited? Yeah. We visited, well, B's already been there, and then we visited E, so that's all set. And so F is now done as well. We can pop F off the stack. So I'll go back to eraser mode. Cool. And now we're back at B, the call to B. So what was B trying to do? Again, I don't know why this is so difficult. Oh no. There. So now we're back at B. B was trying to visit all of its adjacent things, right? That was the D and the F, and now it's finally done. So B can pop itself off the stack now. B's also finished. So I'm just gonna use my mouse because I know it won't let me use my tablet. There we go. And so now we're back at A. And A, what's it trying to do? It's trying to recursively visit all of its adjacent vertices that are unvisited. So it was in the loop. It was like, all right, I'm going to go through B, visit in B, then I'll visit C, then I'll visit E. So it needs to visit C next still, right? You see that? And it's going to try to visit E, but it's already been visited. So that one's happy because that was gotten at from some other direction. And so now we're going to recurse down to C, back from A, because that was the other thing. It was going to recurse on B and C and E. It finally finished B. So now we're on C. And then, all right, so we're on DFS at C now. C has not been visited, so we'll visit it, add it to our visited set. And that was the sixth thing, and we saw it through A. There's our spanning tree building. And then the one adjacent vertex that has not been visited was G, so we'll recurse down into G there. And that has not been visited, so DFS on G visits G. And we saw it as the seventh and final thing, through this edge from C. That was the only way to get there. And then any adjacent vertices, we'd recurse on them if we haven't seen them before, like C, for example, but it's been visited. So we're done. Pop that off. Now we're back in C. It needed to visit G only, because A has already been visited. It's done that. So C is now done recursing on all of its children. And then finally, we're back at A. Excuse me. And so it was trying to visit all of its children recursively that were unvisited. So the B, the C, and the E. The E's already been dealt with, so we are done. And so now A is finished as well. So back, we finally returned, and we computed, see my blue edges there, we've computed a spanning tree. And was it the same one? More or less. Yeah, I think I did things in a slightly different order, but that's okay. I think I went to E first for some reason, but that's fine. That's not a big deal. Yeah, so that's how that works. And it's going to build you a spanning tree. So hopefully that makes sense to you, and you see how useful that is. Now I want you to try. So let's say that these are our two graphs. This is the same graph reproduced twice. I'd like you to draw the spanning trees that you get by traversing this graph starting at A. Let's say we're starting at A always, using BFS and DFS. All right, so let's do one for BFS, one for DFS, and assume that the neighbors are considered in alphabetical order. Okay, so like you can recurse in alphabetical order or add to the queue in alphabetical order when you have options. Okay, so give that a try, and let's do, I'll do BFS first. So breadth first requires a queue, and just while it's not empty, just add the thing. So let me draw the queue like this. A is added to the queue first. So here's A, visiting A. And then we have 3 edges to B, E, and F, and we're going to do it in that alphabetical order. So B is going to be the first thing. We're going to push all the children, right? B, E, and F. And like pop A off. And that's what the order in which we're going to visit things. So we're going to visit B, push any of its children. We'd be pushing E and F. So like we'd push that again, right? Because the adjacent things to B are E and F. And unfortunately, they're already going to be visited, but we don't know that yet. So there's those. And yeah, so that's what you would do at B. We just saw that. We added that edge there. So our spanning tree is slowly building. We added all of its unvisited adjacent vertices in alphabetical order, E and F. But they will already have been dealt with, so we're just going to end up popping them off. It's not a big deal. So there's that one. And let's see. Yeah, now we're done with B. So now we're at E. E is going to be visited, and we got there through A, if you remember. That's what we were pushing it through A there. So we added this edge. That's how we discovered E. And then we'd push any of its unvisited adjacent vertices to the queue, which would be like A or B in that order, but they've both been visited, so we're set there. And so done with that one. So now we're at F. We visited F, and the way that we got here was through A. That's what was pushed there. So now we're seeing F through A, and then we're going to push any of its unvisited adjacent vertices, and so that would be C and D in that order. C and D. All right. So there's that one. So F is now done, and now we have like E again and F again, but they've already been visited, so we'll just pop them off the queue, and then now we're at C and D. So C gets discovered through F, and we'd push any unvisited adjacent vertices. And technically D is not yet visited, so we're going to have it twice in the queue there. But we're going to discover it through F, though, because that was the first way that we pushed. So now C is done. Now we're at D. We're going to visit D, and that was added through F. So that was that edge right there. Okay, that's those guys. And hopefully you can see the spanning tree that we just built. That's all these blue edges. Whee! Those guys. So the edges that we didn't add were this one, and this one. And then also finally we're done. Like we're done with D, and then like it's already been visited, so we're done with it as well there. So that's BFS. That's how I think about it. And then DFS. Honestly, this is not enough information if you say consider it in alphabetical order, because if you're pushing to a stack, they might push in reverse. But like I just showed you on this one, like you can think about it as recursing in order as well. So maybe we'll do it that way. I don't know. We'll figure it out together. So A is the first thing visited for sure, though. And then we're going to recursively like try to go as deep as we can. All right. And so let's say that we're going to visit. We have B, E, and F to go to, but we're going to do it alphabetically. So let's just do B. So we're going to visit B, and then we're going to recurse from B as deep as we can. Visit anything that's unvisited, like E or F, but in alphabetical order. So recursively DFS down into E now. See how that's going to happen from B? So that was the next thing, trying to go as deep as possible. But now we just go back to A, and so E is done. We got to backtrack to the last place that we had options, and that was B. So now we're back in the call to DFS on B, and then we'll go down to F, right? That was the other thing that we could recurse into and visit. And then again, F has two children, C and D, and it will recursively try to DFS on those two things in alphabetical order. So it's going to recurse down into C. So now at C, which is DFSing, trying to go as deep as possible, it'll recurse down into any unvisited adjacent vertices in alphabetical order. And D is the one thing that's not been visited. And so that's going to be your DFS spanning tree. And do you see how it's trying to go very deep? Like A, and that was like a dead end. And then it went all the way right there. Very long paths then. But that's our DFS tree there. All right, I hope that makes sense. It's a fun little thing, I think. Cool little ideas, lots of pictures to draw today. So there's that. And now let's go back to the idea of spanning trees one last time. Let's talk about, like you have a bunch of options. Like these are all spanning trees, BFS and DFS, they create spanning trees. You might want the minimum spanning tree because like you are trying to save money, right? So spanning trees already are saving you edges, but you might want the minimum number of edges to ensure connectedness. Like you don't have to buy as many wires, as much cables to make your network connect everybody. So a minimum spanning tree, MST for short, is when you have a weighted graph this time, so weights are involved. It's a spanning tree whose weight is no larger than any other spanning tree. So there might be multiple minimum spanning trees that like give you the same weight total on your edges, but yeah, we're looking for the minimum one, all right? And you can also talk about minimum in terms of number of edges by just weighting all of your edges as one unit of cost. That's totally fine. This minimum spanning tree algorithm will give you the minimum number of edges if you do it that way, all right? But in general, we're going to consider a weighted graph, all right? A weighted graph, and I'm going to teach you one algorithm. There are a couple algorithms, actually, a couple popular algorithms that compute minimum spanning trees, but the one I want to teach you in this class is called Prim's algorithm, and it's going to find a minimum spanning tree, and here's the algorithm. It's a little weird looking, but let me at least talk about the intuition behind it. So, intuition. When you're trying to find a minimum spanning tree, right, you're trying to connect everybody. So that means every vertex of your graph better be in the minimum spanning tree somewhere. It's just like, which edges do we pick? And so every vertex is going to be there. So like it doesn't really matter where we start because that vertex will be added eventually, okay? And then what Prim is doing, if you see this, like start it on any vertex. Just pick that one, add it to our T. So like here's we got some, like here's the first vertex or something. And then you're always going to try to consider the edges with one endpoint inside of your T and one endpoint outside of T. All right, so what you're going to do is you're trying to add the minimum edge each round that expands your tree outward, okay? And that's just like, it's going to make sure, right, if it's the minimum, you're not going to have any better way to get to your other vertices, right? So let's say that you've built up a minimum spanning tree so far on most of your graph, on a decent amount of your graph. Like here's your minimum spanning tree so far. And that's called T, right? We're keeping track of that in something called T in the algorithm. And then what you do is you consider all the edges with one endpoint inside of your spanning tree, so like one of the vertices of your tree, and then one endpoint outside. So like these are all the edges that you could add to your spanning tree to make it longer. See that? To make it longer, to make it go other places. And what you're going to do, right, because that would like expand it to a new vertex that you haven't seen before. That's what you want to do every time. And then you're going to find the minimum one of those options, right? The minimum one is going to expand your minimum spanning tree in the smallest way possible. You see how there is a rigorous way to prove that, but it's like, all right, this is the one. This is the minimum one. I'm going to add that one. I'll make that in rainbow. That's the minimum. And that's going to advance my tree to be a little bit bigger. And then I'll start considering all the edges out of that one as options in the next round. So that's what it's doing, okay? Find the minimum weight edge that expands our frontier of a spanning tree and add that into our tree and that edge, all right? So as long as you just keep adding the min edge, there's no better way to get to there from where you've been. So that's the algorithm. It's not too hard to to explain in words, but it is a little hard to write down in code. But I'll show you some code in a second. But yeah, let's go through some examples, because honestly, this code is really easy to draw. All right, so let me show that to you. So let's use Prim's algorithm to compute the minimum spanning tree for this particular weighted graph. So what we're going to do is compute a spanning tree that has the minimum sum of weights across the edges that we choose to make up our spanning tree. All right. So let's say that we're going to start our algorithm at vertex A, but it is arbitrary. You don't have to start anywhere special. But let's say we're going to start at vertex A to build our spanning tree. Okay. So there we are at A. And what we do is we always consider, like, this is our tree so far. That's our spanning tree so far. We consider all the edges that cross that boundary between in our tree and out of our tree, because that's like going to build a bigger tree slowly. So we have those three, right? We have a 0 length, a 10 length, and a 9 length. Oh, sorry, and 11 length. And we're going to pick the minimum one. So naturally, we're gonna bring in the D, because that's like the minimum way to get to D and expand our tree and make it bigger without adding too much weight. So like D is the one we picked next. See that? And so now our spanning tree so far looks like this. And now again, we consider all the edges coming out of each of these that are not yet visited, right? So you got the 8, you got the 10, you got the 9, you got the 11, and it looks like the 8 is winning. So that's how we're going to discover F and add the F to our spanning tree. So that's what's going on, right? Just like add the minimum weight edge each time and add that into our slowly built up spanning tree. So 8 was the best thing coming out of each of those. So one edge in the tree, or one end, one vertex in the tree, one vertex outside the tree. That was the best one to go through. That one right there. So now we're at F. We have our tree that looks like this, right? And now we're always going to consider edges, because we're building a tree, right? That where one edge is inside, or one vertex is inside, one vertex is outside, like this one, for example. We are never going to look at this edge right here. Do you see that? Because that's just going to connect our already connected stuff. That's going to make a loop. That's unnecessary. There's no need to ever look at that now. It's always only consider the edges where one's inside the tree so far and one's outside. All right, so the edges that we can consider are the 10, the 3, the 6, the 11, the 12, and the 2. I believe it is the 2 that will win right now. Seems right to me. So 2 is what we're at, and we're discovering H. That was the minimum option. See that? And so now we have even more options. We have, let's see, we have G there through that one, but 1 is looking the best right now. What are our other options? We have the 3, a 12, a 7. Yeah, I think the 1 is going to win there. See that? So yeah, the 1 is the best option of all the vertices inside the tree and one outside. So next we discover our G, and then now we have to keep expanding the tree. So we've got all these guys so far, and like we have to keep on adding edges. So like we could add this one, or this one, or this one, or this one, it seems. And I think the one with the 3 is going to win. That one. So E is the next one. So that's the edge we're going to add into our minimum spanning tree. And do you see how it's like it's creating a spanning tree of minimum weight, minimum total weight. And so there's E that we have there now. And now we have to find a way to get around. And so looking at all the edges, it's like that are one inside, one outside. We got this one, and I think it's just that one as well. So the 5. The 5 is the smallest at the moment. So we see the C right there. And then just like we have to get to B somehow. Which one are we going to use? It's either this one or this one. That's the 4 that wins. So do you see how it's going to create a tree? Just naturally, the way that works is never going to make a loop, because it's always one in, one out. One inside our tree, one outside our tree. And so then we added that one. We just visited B, and this has created a spanning tree. See how it's spanning, connecting everybody with the minimum summed length of all the edges that we chose. And so that's Prim's algorithm. All right. So that's a fun one. And so here's the algorithm again. Here's our example. Now you try. So use Prim's to compute the minimum spanning tree for this weighted graph. Got some negative numbers now, which is totally fine. Like you get a deal. It's on sale to make this edge from this network cable from this computer to this computer or something. That's pretty nice. So try this one, and please start at vertex A, because that's going to lead to a deterministic answer that I can show you my answer to. Okay, so there's A. So give it a try starting there. All right, so, well, what are your options? This one, this one, and this one, right? I think 0 is the winner, for sure. So we're going to discover E next through this edge right here. Maybe it's hard to draw a line in this particular direction. Cool, so now our tree looks like this. What are we going to add? What are our options? We got like -1, 7, 1, 2, 0.5, 0.7. I think the -1, right? That's a good one. So I think -1 wins next. So we're adding in G. And then everybody else, I think, like these are all positive over here, like connecting positive, positive, positive. Positive. I see another -1, right? It's like this negative as well. Like we're definitely going to prioritize that for sure. So negative, get us to here. And then again, like the only one like where one is inside, one is outside, and I see negativity, and again, that's beautiful. That's the minimum weight for sure. So like you do have a bunch of options right now. You see them all. So many options with one vertex inside the tree, one vertex outside the minimum spanning tree. But this is the only -1 I see right now. The only negative option, and so totally we're going to take that one. Oops. So add in the J. Cool. And now I have to pay more attention. So let's see. What are we going to add? What are our options? I see a 3 that we could do, a 4. 3 is still better. I see 0.7. That's winning so far. So 0.7. Oh, 0.5 is even better than that. 0.5. Anything better than 0.5? 1 and a 2. Yeah, I think the 0.5 is what we're going to take next. And you see kind of like the rationale for all these. Like these are a bunch of negative weights that got us to here. Like maybe there was another like 0.25 from here or something leading us to here. It's like that would have been the better one to add. But no, there wasn't any of that. So 0.5 is the best way to get and expand our tree into B there. And then, all right, what else we got? We have, I see a 4, I see a 3, so 3 is better than 4 so far. I see a 1, that's pretty nice. Maybe the 1's the winner. 1 versus 2 versus 3, I think 1. Well, this is the next edge we're going to add. It's always on the edge level. We're adding edges to this tree. So there's D, and there's a -4.1, and I'm just like immediately going to add that one because that's like the smallest thing ever. That's totally going to add that one. And now it's like, do we add the F or do we add the H now? It's like we have a 4, but I see a 3 to get there. And that's the best way to get to that F. It's not 7 or 11, right? So 3 is going to be the one that we add. You can see kind of intuitively why this is going to make the minimum spanning tree. There's that one, and then we're kind of stuck for H. The only way to get to H is through the 4, and so we're forced to add this edge in to our spanning tree, which kind of sucks. Like maybe this is very expensive. Like this is 1,000. You're forced to add this edge because this is the only way to create the full spanning tree. See that? So there's that one, and I think yeah, that's the answer. So yeah, hopefully you got that. That I think is the only. There are multiple spanning trees sometimes, but if you start at A, I believe this is the only one that you could get, because they would have to have the same minimum sum. So let me show you prims and racket actually, and I'll prove to you that it's the same exact thing that it finds if we start at A. So here is a racket program called prim, and here's my graph G. I've created it in racket as a list of lists, as a list of pairs, right? Where the first thing is the name of I'm doing this as an adjacency list, right? This is a graph stored as an adjacency list. It's this graph, and like for A, for example, it's like A, what are its neighbors? We got C, E, and B with lengths 3, 0, and 0.5, and I'm just keeping track of all that. So there's B, C, and E. I'm just doing it in a nice order, I guess. 0.5 to get to B on that edge, 3 to get to C from A. See, that one with the 3. So I'm just storing all that information. E to get to there, like F, for example, has 3 edges out of it. D getting at 11, E with 7, and J with 3. E with 7, J with 3. So I programmed the entire graph. That is now stored in there. So that's the graph itself. And then here is here's the prims algorithm. So I'm essentially programming this. So first, RT is the empty set. So I'm actually you can create a set in racket. It's the type mutable set because I want it to be able to change. So I'm keeping track of our spanning tree in terms of its vertices and edges. So I'm keeping track of the vertices set that's in our spanning tree, minimum spanning tree, and the edges set. So they're both empty sets right now. Started as emptiness. And then I do need the length of G, because that's like a loop here. Like I need the size of G, that's n. And I want to do that n minus 1 times. So the first thing we do is we want to add a vertex starting somewhere. Pick any vertex and add it to T. And so I'm going to add in just the first thing in our graph, add it to the set of vertices. No edges, right? Because it's just the vertex itself right now. And so that's going to be the A. So I'm adding the first thing. That's me adding the A. And then I'm going to loop n minus 1 times, and in racket this is inclusive, this is exclusive, so it's going to loop n minus 1 times. I gets to range it between 1 and n minus 1. And then I'm going to print out I, and then I have some helper functions like, let me get all the edges across the boundary where this is my T so far, and this is the full graph G, so that's going to give me all the edges I could use, right? And then I want the minimum one. I want the minimum length edge, minimum weight edge across that boundary, so I also made another helper function. Like, give me the minimum edge across those, of all those edges across the boundary, and like, that's the one. That's the one I'm going to add. So add that edge into T edges, and then also adding that edge adds a new vertex into my tree as well. So like, that's my min edge that I'm considering right now, and it is going to be one side of that was the vertex that I needed to add into this graph. It was either the first or the second thing in the pair, right? Because it's an edge, and well, it doesn't matter because I'm going to add it to a set, and so there's no duplicates. Like, I'll just re-add the thing that was already there. It's not a big deal. So that's fine. And then what I'm returning, did I mess something up here? Do you have? Yeah, this is fine. I don't know why this is coloring this weird, but like the return value is T edges, right? So I'm going to return the tree, right? I'm going to return the tree as the list of all the edges, the set of all the edges, because we can just draw that. I can just draw all the edges in like that. That creates the tree. So that's what prims does. And like here's it figuring all the edges across the boundary. It's like, all right, here are the vertices on in my tree so far. And like I'm doing some weird looping through the tree. You don't have to worry about it too much, but like that's what that's doing. And then the min edge, what I'm doing is I'm sorting it. I guess I could have done this in a faster way. This is like n log n now. Could have been O of n if I wanted it to be, but this is an example for ease of reading rather than efficiency's sake. So I'm sorting all the edges, and then I'm just giving back the first one. That's the minimum edge. All right, so what I'm sorting it by, the third thing, which is apparently that's going to be your weight. Okay, so that's that. And so if I call prim, it's going to print out the edge. It's going to return the edges back, and also print out some work with the printf calls here. But it'll give me back the tree at the end of the day. So that's the code. Study it some more if you'd like. But let's call it and see what it does. Whee! So there it was. There it goes. And so like when I is 1, it's adding in from A to E. Cool. It's like that's the one. That's the one we added too, right? A to E. A to E. Like there's A, then it added in from A to E. Oops. And then the next round, like this is the entire set of all the edges, and you can use that to create the graph as well. That's what it's finally returning, but I'm also just printing out what it's saying. And then we go from E to G. That was the best one. E to G. That's what we did too, right? That's how the algorithm works. And then G to I with the weight -1. Of course, that's going to win, right? G to I, -1. That was a bad squiggly line. And then I to J, -2 for sure, right? There's that one. It's fine, didn't it? Then A to B, 0.5. Yep. And then D to E1. That was the good one. Where is that? Is this one? Boop. So we've added that one in now. And definitely D to C, -4.1. That's like the definite min edge now. For sure, now we have 2 last options. Do we add an F or do we add an H next? And it looks like F to J with 3. That's the good one. And then we're forced, our hand is forced for the last one, just to complete it. G to H. The weight for edge. And that is exactly the thing that we calculated with our hands. Alright, so that one was deterministic. There was no 2 options that gave us the same minimum edge sum. there really only was one minimum spanning tree starting at A there, and probably starting anywhere else as well. But you never know. Let's see here. So yeah, I think that's what I wanted to do there. Or actually, let's see. Technically, no, you're right. Yeah. No, I don't want to say anything. I thought I saw a different one, but no. So let's see. I think that is everything. So yeah, study this code if you're interested. Try to code it in C++. That's a good thing to do. But like, get your graph in adjacency list order, and like, you can kind of read this code. It's not too bad. This stuff is a little weird. This is like looping through lists for every element of a list. Call it this. But you can look into it. Checking if things are sets, for example. It's kind of self-explanatory racket code, but you can look it up if you need to. But that's minimum spanning tree stuff, and that is officially everything that I want to tell you about trees. So that's exciting that we finished that set of slides. We'll be moving on to a next set of slides on a completely different topic in the next lecture, and I guess I'll see you then.